Hey guys, can I get a sound check? Thanks, Jimmy. Okay, guys, let's get started. So the first thing I wanted to do was to show you guys this, what's known as a data sheet. To make a few points. So data sheets are like if you were going to go buy a single bipolar transistor, you know, to use in the lab, etc. This is what they would sell you. So this is the user, I don't know if you call it user manual. The data sheet sort of says what to expect. Okay, which, you know, it's got a lot of useful stuff in here. Excuse me, but what I wanted to show you, and this is just some bipolar transistor, okay? So I think the main thing I wanted to show you guys was that, you know, it's going down and there's different characteristics. And like one of the ones we're familiar with is the DC current gain. So that's our beta. Their symbol for it is HFE. Okay, but the thing I wanted to show you guys is look up here. So there's the symbol. I don't know if you guys see my cursor, but see the symbol, you see min, max, and unit. And the point I wanted to make is that, for example, you know, these transistors we're talking about, whether it's a bipolar transistors, MOS transistors, they're some of the most precisely made devices that mankind can make. Okay, but unfortunately, no two are the same. I mean, look at this beta, which again, they're using the HFE as the symbol for it, but they're giving you a minimum value and a maximum value, or just a minimum value, meaning that the max value might be anything. So for example, at a collector current of 10 milliamps and a VCE of 1 volt, this device here has a minimum beta or HFE of 50 and a maximum of 150. So means you can't, like, you got all your designs have to deal with like really major variations in you know these devices, because you know you can't tune every circuit you build. I mean, you can do it while you're doing a lab in Cal Poly, but not when you're building anything at all, any kind of product as a professional engineer. So a major part of dealing with, you know, doing microelectronic design is designing robust circuits that can handle these really big variations. So this is just one of them. Again, beta is one of the things that varies quite a bit in bipolar transistors. This is the same, so you'd buy, you know, 10 of these, and these are not different model numbers, right? This is the same model number thing as if you buy a Tesla and they say, well, the range might either be 200 miles, 100 miles, or 300 miles. That's what they're kind of telling you here. So get ready to like deal with it any way you can. So, you know, this is sort of very typical. So that's one of them. What was the other thing? And you see, like, there's a lot of other parameters, but I think that was a major thing, like the base emitters voltage. They're at the same current. It can vary between 0.65 and 0.85, depending on the device you may end up with. Another thing I wanted to show you guys was there's like lots of interesting curves as well, but Another major variation is variation with temperature. So here you have, also we didn't discuss this, but beta, so this figure 15 also shows beta with respect to the collector current. And first of all, at each temperature, this beta is changing with the collector current. So at very low collector current or very high collector current, you get actually very low beta values. There's kind of a sweet spot, out here, in the 3 to 10 milliamps, I guess, where you have a reasonably high beta, but things tend to drop off. This is normalized beta, so it's not like really beta 1, but you can see how things drop off at different collector currents. And notice how much of a difference you get at different temperatures. So 25C is roughly, I guess you can think of it as being room temperature, and 125C is pretty typical by the time you talk about your device itself heating up. Like in a consumer application, the junction temperature of your device may easily be at 125C. So that's almost a 50% right there variation over those temperatures of beta, just as a parameter. Even if it was a same device, as you heat it up, its beta is going to change quite a bit. And all these other parameters are also changing over all this stuff. So again, it's sort of emphasizing the importance of doing a robust design that can handle a lot of variation. So that's a lead up to our discussion today about biasing. Because a big part of your work as as engineers, let's see, you're sharing your screen. So a big part of the design, when you actually get to working in the industry or really, building anything real, is dealing with these variations and making stuff that will work over all these variations that are possible in like typical devices you buy. Okay, so now let's talk about, we talked about last time, we talked about the input-output impedance, and today we're going to talk about biasing. And a lot of the reason I brought up the data sheet and these variations is a lot of the differences in the different biasing circuits, or how well they can deal with these variations. Because you can do a really simple bias circuit, as you'll see, but it might not do well in a real situation because it's just really tuned for one particular spot. Okay, so let's go to our slides. So just a reminder what biasing means is, we want to basically operate our circuit. Let's say we have our gain, common emitter gain stage. We want to make sure we bias it at a particular point. If we don't bias it properly, then this guy's not going to be in forward active mode, and it's not going to do what we want. So if you look at how your input will look as a function of time, is you'll have, it's not necessarily a sine wave, but let's say if you had a sine wave as an input, it would be riding on some, you'd want it to ride on some DC voltage. You don't want it to be down here. Because over down here at 0 DC voltage, this VB, this V base emitter voltage will be very low, so have very low current. You're not going to get any gain out of the circuit. You wanted this to be, approximately at VBE of, you want the VBE, the DC value to be, around 800 millivolts. Well, anywhere between 650 to 800, 900 millivolts, depending on how much collector current you want. Again, this would mean that your collector current will be sitting at some bias point. You'll have some DC value, and it'll have variations around it. So that's what we want to create. We want to create we're looking today at how to build these different bias circuits, because you will not be, a battery or a voltage source is not going to be available at a reasonable cost, at a reasonable size, in large volumes like you would need. This next slide is about DC analysis, small signal analysis. I think we've already talked about this quite a bit, about how batteries are like shorts, or voltage sources are like shorts, currents are like opens, and how you go from DC to small signal. Okay, so let's look at the first example, okay, of a bad biasing circuit, which is basically no biasing. So this is giving us an example of somebody's hooked up, and there's every tendency to do this. I've done it myself. You say, okay, I need to gain up some signal. You remember that this circuit here, this common emitter circuit, is an amplifier. So you take your device and you plug it into the input of the amplifier you build, and you get nothing on the output. And you wonder why. The reason is, this thing, again, this microphone is giving out a small voltage, but it's not sitting on top of a bias. So whereas we want, again, the time, we want to be sitting up here, we want our input to look like this with a certain V bias. It's kind of sitting what this circuit is kind of sitting like this down here, where it's got zero bias, and you don't get any current. So let's take a look at that, what that does as an example. So if you look at it from a large signal standpoint, so if you look at it from large signal view, we have a kilo ohm resistor, transistor Q1. We have our V out. We have this VCC. And we've got our microphone going in there. So let's, for the sake of discussion, say output. So assume that output of mic is around 20 millivolts. Okay, so this is the microphone is outputting. So if I'm speaking into this microphone, with respect to time, this guy is outputting something that's got a maximum value of 20 millivolts coming out. And I want to amplify that to something bigger out here. Okay, so let's see what happens in the case where you've got it just connected directly to the input without any other thoughts. Okay, so in this case, we've got a 20 millivolt swing. Let's say we've got a bipolar transistor with an isobes of 6 times 10 to the minus 16 amps. And so this gives us a change in collector current of IS exponential of delta VBE over VT. And that's equal to 1.29 times 10 to the minus 15 amps. So this delta VBE is equal to 20 millivolts. So that's all the stuff you see. Okay. So if I look at the change in the V out, so delta V out is going to be this delta IC times R sub C. So it's 1.29 times 10 to the minus 15 amp times 1 kilo ohm. And that is equal to 1.29 times 10 to the minus 12 volts. okay? So this thing is anything but gain, right? So I gave it like a 20 millivolt input, and my output is 1 times 10 to the minus 12 volts, which is basically 0. You can't even, I don't think you can even measure this thing without like specialized, very, very specialized equipment. You certainly couldn't measure this value in the lab, right? So you do something like this, it basically is going to look like you've got your microphone sitting here and the output is just sitting at ground essentially. It's not going to be moving at all. Okay, this you can't, this delta V on the output of something times 10 to the minus 12, I don't know how you'd measure such a thing. And if you think of it as the gain, so-called, so if this is delta V out over delta V in is 1.29 times 10 to the minus 12 volts over 20 millivolts. And that is equal to 6.45 times 10 to the minus 11. So that's like a huge attenuation. It's not gain. You're basically taking your input and you're basically completely snuffed it out. Okay, by connecting it, by not basically biasing, by connecting it directly to the input of your amp. Okay, so this thing is, I'm going to guess at least some of you guys, even after this class, you're going to do something like this at some point. So I've done it, just not thinking it through, right? Just hook it up straight. You're not going to get anything coming out because you don't have a bias. You haven't created a bias in input. So what you really need, let's say if you could bias it with a battery, which we can't, but just to see what you'd really like to get. Let's say you had a bias of, so if you want to repeat this thing with a 0.65 volt battery, so you copy it over. So this is what we'd really like to do. In the ideal situation, we can't, but just like for the sake of discussion, let's say you put a VBE of 0.65 volt DC value, or V bias, let's call it, V bias of 0.65 volt here. Let's see what we'd really like it to do. So in that case, our delta I is going to be I sub S exponential of, so it'd be V bias plus delta V in over VT minus I sub S exponential of just V bias when Vn is 0. Okay, so it's going to be those two differences. So what I do here, what I just did by putting this battery here, is I took this guy, so by doing this, I took this situation and I changed it to, I put this input, this is not to scale, so I put that input up here at a bias voltage of 650 millivolts. Okay, so the same signal level coming out of the microphone, but I just bumped it up to be sitting at a bias level of 650 millivolts. So my change in my current, I have to include that bias voltage. And when there is a high value of a signal, it's added to this delta VN. And when there's no signal, let's just say it's V bias, or you could think of it as V bias minus delta V. But either way, so here this would equal to, so IS, it would be exponential of 670 millivolts over 26 millivolts minus exponential of 650 millivolts over 26 millivolts. And all this would give me 93 microamps minus 43 microamps, which is about 50 microamps change in current. So my delta V out, again being R sub C delta I sub C, is 50 microamp times 1 kilo ohm is equal to 50 millivolts. Okay, so I put in if I bias it at 650 millivolts, I put in a 20 millivolt signal, I'm going to get something that's about 2.5 times bigger. So the output's going to look like that. So at least it's gained up. Okay, so my gain for this is going to be 50 millivolts over 20 millivolts, or 2.5 times. So at least I'm gaining it up by biasing. So this is what I'd like to do, but like I'm saying, this is an ideal situation. So I have to find some way of replicating this without using a battery. Are you guys able to follow what I'm trying to say here in terms of biasing? So here we haven't biased. We get basically nothing because we don't have this bipolar transistor operating in the right region. So this is, don't do this. You need a biasing circuit to put yourself in a winning scenario. And now, something though, this is what you like, but I'm saying that it's, this is difficult to get. Any questions about that? Okay, so let's see. So here's the next thing you might be tempted to do. You might be tempted to say, okay, well, I'm gonna, this thing was this input when I had no bias. So when I just had this, right, in the previous example. So this point was too low. I'm gonna pull it up. I'm going to connect it to the supply voltage. So that's also like a really bad, I don't even know why they bring this up in the book, because it's obviously a very bad idea. All you've done is like shorted, you've got this voltage up. So certainly your VBE is a high value. So one problem you have, which is not your biggest problem, but it's a pretty big problem, is depending on your VCC, so if this VCC is like 1.8 volts or 2 volts, your VBE is going to be huge. So you're going to have like a huge collector current. So you already have that problem. Even if you somehow didn't have that problem, all you're doing is you're really shorting this input to a supply voltage. So the signal is just going to be shorted. So this is a non-starter, obviously. But basically the idea is, hey, I want to pull this up somehow. So the next idea is, okay, why don't I pull it up with a resistor? So when I pull it up with a resistor here, so it doesn't go all the way up to VCC, but goes to where I want it to go. So this is what, so let me just draw it like this. Let's see. This looks awful. I'm not going to copy this. I'll just draw another awful schematic to replace this awful schematic. So basically the idea is this. You got your amplifier. And you put a resistor here, and then you put your microphone. Oops. And the idea is that you know, maybe this resistor by, you know, some value. So basically you're going to have this base current going into here. If you get the right delta V across this resistor, so let's say this is R sub B. So if delta V across this R sub B is equal to something, like I guess if this was 2 volts, so you'd want that to be 1.2 volt drop from here to here, then you'd get this at 0.8 volt bias. So then you're good, right? So the idea would be to have I sub B to be something where, you know, it gives you the right voltage drop across here. Everybody's able to follow that? I'm not getting feedback from you guys. Come on. I think I'm gonna pick on somebody. Be careful.
Someone asked you to repeat it.
Yeah. Yeah. So let's see. So Jihoon, are you trying to, do you see what I'm trying to get to?
Yes.
So basically the idea is, what I'd like to do is this. I want to get this guy to somehow have a DC voltage of 0.8 volts-ish, right? And I want to have my input signal from the microphone. So let's say that's 20 millivolts. I'd like that to ride on this 0.8 because, you know, that puts me in the right place for this amplifier to gain up this 20 millivolts properly for me. So I'm looking for a way to do that without putting a battery here. So I'm gonna say this, okay? So at 0.8, so at 0.8 volts, Q1 is gonna have a certain I sub C. Okay, so there'll be some I sub C that I want, okay? And that I sub C is gonna be I sub S exponential of 0.8 volts over 26 millivolts. You follow me so far? June? Okay, so that's the collector current I'll have. That's what I want to have. Okay, so at that collector current, I'm also going to have a base current that's going to be that collector current divided by the current gain. So let's just, for the sake of discussion, say beta is about 100, average beta. Okay, so I'm going to have I sub C over 100 is going to be this I sub B going into this. So this leads me to think, you know, if I wasn't thinking about this too clearly, that, hey, maybe what I can do is use this I sub B to create a bias, because what if I create a put a resistor here, okay, and this I sub B is going to flow through this resistor into the base, so that way I'm going to get a voltage drop. Let's say VCC is 2 volts. If I can get I sub B times R sub B to be 1.2 volts, then this VDC is going to be 2 volts minus 1.2 volts. So that's going to be the 0.8 volts I'm looking for. Does that make sense?
Hey, Professor, my connection was lagging when I first joined. In the schematic, what is the thing just bottom left of the RB resistor? Yes, what is that?
Oh, sorry, that's a cheesy symbol for a microphone. So we're all the examples in this section, don't ask me why, in the book are like, I think it's just so that it's everybody can connect to it as a microphone driving this input.
Got you. Okay, so that, okay, thank you.
Sure. So this guy is a microphone. And so we're saying a microphone typical output is around 20 millivolts. So what it'll look like is
That cleared it up for me. I just wasn't sure because my connection was bad.
okay. So I was just gonna so it's basically something that changes with time, and the sort of the maximum value is 20 millivolts, just because a microphone just can't be pumping out a lot of voltage. It's just a mechanical device, works with your voice, sort of works with air pressure, I guess. And so it's just not pumping out a lot of voltage, and you're trying to like gain that up. And it also, that voltage is also not riding on a bias voltage. It's just plain old 20 millivolts sitting on ground, basically over 0 volts. So you got to somehow bring that up in a, in some kind of way to make it so that you can gain it up, so that you can use an amplifier following it. Okay. All right. So this is the thinking here. Okay. If I can put, if this transistor was, if I could get this to the right bias point, this transistor would have a certain base current, which means that I could get that, use that base current to actually get this to the right bias point, because you'll have some base current flowing through a resistor, and that'll have a certain voltage drop. And if I tune this resistor right, knowing I sub B, I can get this to the exact voltage I want, right? So simple calculation. So let's do it. Let's do an example. All right, so let's do, so let's say VCC is 2.5 volts and R sub C is 1 kilo ohm. And this guy, let's call this voltage, this DC voltage V sub X. And I'm not going to draw the microphone for now because I'm just thinking about the biasing. So let's just look at the biasing circuit. Okay, and the microphone would, if I did draw it, it would kind of sit here, right? It would connect to here, and you're basically pulling, you're making its input right on top of this VX. But let's leave that out for a second and just look at the biasing. Okay, so these are the values I select. So the idea is, again, that with this transistor on, there's going to be a certain collector current running through this. And so that certain collector current is going to have a certain base current, and I can use that base current to drop just the right voltage across a resistor from VCC to get this to the right voltage, so it has the right collector current. So it's kind of, again, this iterative way of, of how this works. We're saying if this was at the right voltage, this would have a certain current, and that certain current would give me a certain current here, and it would put this at the right voltage. Okay, so let's see how that works. So I sub B, okay, let's say, so V sub X is VBE, right? So this is also the base emitter voltage. Okay, so I sub B is going to be the VCC, so it's gonna be this minus this divided by this guy, okay? So whatever voltage this is, minus this divided by this is gonna be I sub B. So VCC minus VBE over R sub B. So that's our base current. And the collector current for this guy is gonna be beta times the base current. So that's gonna look like beta VCC minus VBE over R sub B. All right. Okay, so that's VBE. And now if you look at VCE, so this is VCE for this device. So we got to make sure this is at forward active. So we also have to calculate VCE once we're done. So the VCE is going to be VCC, it's going to be this guy, minus the voltage drop across R sub C caused by IC. So it's minus I sub C, R sub C. So it's equal to VCC minus beta VCC minus VBE over R sub B times R sub C. Okay, so that's this voltage VCE here. Okay, now let's see, let's try some examples. So let's assume, so this is example 5.7 from your book. You guys want to look at that, but I'll go through it. Assume that I sub S is 1 times 10 to the minus 17 amps. Beta is equal to 100, and of course VCC is 2.5 volts. Okay, so because we're in this situation where we're assuming something for V sub X to get a collector current, and that collector current gives us a base current that gives us V sub X, we have to calculate this in an iterative way, right? Because we are assuming a certain starting point with V sub X, but we aren't sure what it is, okay? Because everything's like affecting everything else. So as usual, we start with our first guess. Is VBE is 800 millivolts. So we plug that in to get I sub B. So that's 2.5 volts minus 0.8 volts over 100 kilo ohm. Oops, 100 kilo ohm, and that gives us 17 microamps for I sub B. I sub C is beta times I sub B, so it's 100 times 17 microamps or 1.7 milliamps. Okay, and that assumption. So now we're going to see if what VBE this gives us, okay, to this iterative solution. So VBE is VT natural log of I sub C over I sub S. So it's 26 millivolts times natural log of 1.7 milliamps over 1 times 10 to the minus 17 amps. So this is equal to 850 millivolts. Okay, which is pretty far from our original guess. So this first guess was pretty close, but it's enough. It's not close enough that we can stop iterating. Okay, because if you guys remember, a 60 millivolt change in delta VBE would give us a change in current of like a factor of 10. So this 50 millivolts is a pretty big change. So we got to try a second iteration. So iteration number 2, we start with this VBE of 850 millivolts and calculate I sub B again. So that's 2.5 volts minus 0.85 volts over 100 kilo ohms. And that gives us 16.5 microamps and gives us an I sub C of 1.65 milliamps. And now if you plug this in back into VBE, we end up with 1.65 milliamps over 1 times 10 to the minus 17 amps. So this gives us 851 millivolts. Which, so this one iteration was pretty close to this guy. So this is close enough. So that's what it is. Okay, so basically we end up with I sub B of 16.5 microamps and I sub C of 1.65 milliamps. And that gives us a VBE of 851 millivolts. We double check the VCE just to make sure we're in forward active. So VCE is 2.5 volts minus this R sub C is 1 kilo ohm minus 1 times 10 to the third ohm times this collector current 1.6 milliamps. So this gives us 850 millivolts. Okay, so VCE is roughly equal to VBE. Okay, so if we have VCE roughly equal to VBE, we're still in forward active. So everything looks good. And then we can sort of calculate our G sub M is what is that? Is I sub C over V of T. So it's 16.5 milliamps over 26 millivolts. So so it's 0.63. Excuse me.
That should be 1.65 milliamps, right?
Oh,
Not 16.5.
yeah. Thanks. What have I done? Yeah, right. So this is 16.5. Sorry. Thanks. Whoever mentioned that. Was it?
That was me, Brandon.
God bless you, Brandon. Thank you. I was about to go off into the weeds. Let's see. So what does that do for us? 1.65. So that gives us 0.2635 Siemens or 1 over 15.75 ohms. So our gain, our small signal gain is GM minus GM RC. So that's 1 over 15.75 ohms times 1 kilo ohms. So that's roughly a gain of 63 times. Okay, so cool. So I gotta basically by using this upshot. So end of story is by using this really simple biasing technique of just hooking up the right, a pretty big value resistor to the base. I got this guy nicely biased up. So it's got this 1.65 milliamp current going through it. It's, in the forward active mode. because of the VCE is, same as VBE, good. And I got a nice gain of 63. So now, if I put my microphone with my, 20 millivolt input onto this thing, so the delta V out is going to be like 1.26 volts. So great. Like I'm going to basically amplify my input very nicely if I hook up my microphone here. And notice I only used one resistor. So resistors are cheap, they're small. That's good. So it seems like, this is a good choice. But of course, I only say that because it's not. And, why isn't it? Well, the reason is this is an example of something you can get working in the lab, but not in production. Okay, so you can, in the lab, you've got, a single bipolar transistor. You know what the beta is. You can basically tweak this voltage, resistor R sub B to get the right I sub B going through it, and get this at the right value. But so Brandon, you might have missed this at the beginning, but I was looking through a data sheet for a typical bipolar transistor, and beta, we're saying, even if you buy, 100 of the same model, right? Some of them would have a beta of 50, and some of them would have a beta of 150, and they would basically have a big range of beta values. So this beta for a real product is not constant, unfortunately. There's a range because in production, all sorts of things, as precise as you try to produce something, these things are going to vary. And so if this beta value varies, it really throws a monkey wrench. So, let's say you tweak this thing so it's all stable around this point, and my input is VBE and my output is, VCE is this value. Okay, but what happens if, instead of a beta of 100, the next device I pop in is going to have a beta of 150. In that case, for the same base current, my collector current is going to go up by 50%. Okay, so in the same situation, my collector current is going to end up being, I don't know, around like 2.4 milliamps. And that 2.4 milliamps across this collector resistor would drop my VCE down close to 0. Okay, so this transistor is no longer going to be in forward active mode because its collector value dropped below VBE and significantly below VBE. Okay, so basically this guy has this approach is got 0, it's very sensitive to this parameter beta, among other parameters, but I'm just sort of harping on this parameter beta of the bipolar transistor. And in no way is that gonna be a single steady number from device to device. So if you make 10 of these circuits, of this really simple circuit, you're gonna have to spend a bunch of time changing R sub B values for all 10 of them. And there's no way you're gonna make this product economically. Imagine if in a real product, you might have tens, hundreds of different things that like this. So, you need stuff you can't have circuits that are depending on, or going to break if the beta of your device, is changes, because it's guaranteed to change very much. What's even, what's even worse, or maybe the same, I mean, to further talk about what can go wrong here, is I was showing a graph in that data sheet that even for the same device, the beta changes maybe by a factor of 50% just over temperature, over a temperature where, you know, it'd be pretty typical for a consumer product that you need, your device would need to support. So this device would work at, for one, so this biasing condition would work in one circuit, the way it's designed in the lab. And then even that circuit, if it gets hot enough or cold enough, this thing is gonna stop working. So that's the real problem with this thing. So this is kind of really a good example of the real problems you run into in circuit design, which is the majority of your time, like once you understand the common emitter circuit, you've understood it, right? You're not going to spend, you know, hours and hours trying to replicate this in the lab once you're working, right? Once you've played with it once or twice. But a lot of time, what you have to do is to come up with circuits that are robust, that will survive whatever variations you would expect in the product you're making. That's like 95% of the job, is dealing with like stuff that's not gonna break. And the problem is, you know, in undergraduate labs and undergraduate situations, a lot of times what we're doing is we're trying to tweak one circuit in the lab to, you know, finish some lab project or something, but it's just not a good approach for a product, which is what you guys will be faced with eventually. Okay, so that biasing circuit, not a good idea. Okay, so what should we do? Well, so the next idea is to, why don't we do this? Why don't we stick, we know this base current is pretty small, right? So we want to basically build a circuit that even if the base current changes a bunch, right? So even if my beta varies quite a bit, again, that beta varying quite a bit means my base current will vary quite a bit, I'm still going to get the same voltage. Okay, well, so one thing we know how a voltage divider works. Well, what if we put a resistor here? Okay, so make this R, let's call this R, I don't know, R2. And if this current RB, the current going through RB and R2 is bigger than the current going, significantly bigger than this current I sub B, we can kind of ignore I sub B and just call this sort of a voltage divider, as, you know, set us up as a voltage divider and have a steady voltage. Let me show you what I mean by that. Okay, so basically you end up with this circuit. Okay, so basically what happens is, as you know, a voltage divider here, you basically end up with, you know, R2 over R1 plus R2 times over VCC. And then I sub C is just equal to this V sub X, okay? So voltage divider puts a certain voltage here, and that voltage gives me the correct I sub C. So basically by picking R1 and R2, I can set the voltage here, knowing VCC, I can set the voltage here to be exactly what I want. Okay, now notice there is a big condition here. So big assumption is that IB is very small. Why is that? Is because this equation this equation for the voltage divider assumes the same current goes through R1 and R2. Okay, but that's not entirely the case because there's a certain current goes through R1, but then a little bit of it, I sub B, gets split off and goes into the bipolar transistor's base, and the rest of it goes through R2. Okay, so this equation assumes that we can neglect I sub B. Okay, and what does that mean? That is very small. It means that the current through so I R2 is much bigger than I sub B. If that's the case, you know, this is almost correct because, you know, this small current, if this current is relatively large, the small current being split off here doesn't really move this voltage Vx that much. Okay, so that's what our big assumption here is. Okay, so let's do an example of that. So what I'm trying to do again here is to set up myself in a situation that the exact value of I sub B doesn't matter. Okay, as long as it's small. So I'm saying as long as I sub B is very small compared to IR2, it doesn't matter if it's, you know, 50% smaller or 50% larger. It's always, you know, 50% of a very small value, or so as long as I can neglect it, it doesn't matter the exact value of I sub B. So basically, like having varying beta is not going to hurt me in this situation. I'll still kind of have about the right value. Okay, so that's the upshot of what we're hoping this is going to get us here. Okay, so let's do an example. Okay, so this is example 5.8 out of your book. And so very similar, VCC 2.5 volts. I've got R sub C of 5 kilo ohms in this case. I have a Q1. And then I have my R1 is 17 kilo ohms and R2 is 8 kilo ohms. This is V sub X. So right off the bat, notice one thing, right? In the first example I had here, I was using R sub B of 100 kilo ohms. And the reason I was using 100 kilo ohms was because I wanted to get a fairly large voltage drop from a small I sub B. Okay, I knew my I sub B was going to be fairly small, so I used a pretty large resistor value to get a voltage drop here, to get myself down to roughly 0.8 here. Okay, in this case, notice my resistor values are about a factor of 10 smaller in value. And the reason for that is I want this current to be reasonably large, then that I can be much larger than I sub B. Okay, so I've already reduced my resistor values significantly from that first biasing current. And the reason for that is I want this current to be much bigger than the current into I sub B. Okay, so let's see what this looks like. Again, I sub S is 1 times 10 to the minus 17 amps, and beta is equal to 100. Okay, so assuming, I'm gonna first assume that I sub B, so first assume I sub B is negligible. And I want to solve this. And then I'm going to come back and double check that that was a good assumption. Okay, so with this assumption, V sub x is this guy. It's just a resistive divider equation. It's R2 over R1 plus R2 times VCC. So it's 8K ohm over 8K ohm plus 17K ohm times 2.5 volts. It ends up being 0.8 volts. And that gives me an IC of so it gives me a 231 microamp I sub C. And assuming a beta of 100, that gives me a sub C over 100. It gives me that 2.31 microamp for I sub B. Okay, so let's check what's IR1 is approximately 0.8 volt divided by 8 kilo ohm. So it's about 100 microns. Okay, so IR1 is 100 microamps over 2.3 microamps. So is 43 times bigger than I sub B. Okay, so this current is much so IR1 is much bigger than I sub B. So my initial assumption that I could ignore I sub B is a reasonable one, because it just doesn't, it's not going to change this Vx very much. Okay, now it doesn't matter if let's say my beta wasn't 100, right? Let's say my beta was 50. Okay, if my beta was 50, my I sub B would be like 1.15 microamps. And my IR1 would still be much larger than I sub B. So I would still end up with a Vx of 0.8 here. Okay, now let's see if beta was 150. This would end up being whatever, 3 microamps. And still IR1 is much larger than 3 microamps. So this Vx would still be at like around 0.8. So what I've done with this voltage divider circuit, if I run enough current through this that I can neglect I sub B, what I've done is I have sort of what's a good word? I can sort of ignore the effects of beta on my biasing circuit design. So even if beta is all over the place, this will still bias this guy correctly. So I will still always get 0.8 volts here, and that 0.8 volts will give me approximately the right current. Of course, this is assuming I sub S stays relatively constant, etc. But at least this gets rid of one sensitivity. Okay. Any questions about that?
What does it say on the bottom right-hand side? Is that I sub R1?
Yeah.
Equals, okay.
This one.
So you have I sub R1 on the left and right.
Is much bigger than I sub B. Is that what you mean, or is it another equation?
I'm just confused because you have I sub R1 equal to 100 microamps, and then you have I sub R1 equal to 43 times I sub
Well,
B.
I'm sorry. Yep, sorry. This is a bad one. So basically, this is what I want to say. I just want to say I sub R1 is 43 times bigger than I sub B.
Gotcha. Okay.
So what I wanted to say was really just that I sub R1 over I sub B is 100 microamps over 2.3 microamps is equal to 43x.
Gotcha. Okay. Okay.
Yeah, thanks for pointing that out. Did you have a question? Is it IRC? No, good. Okay. Okay, so this is this second biasing current. So let me just talk about this. So if you, I mean, we don't, this was, you know, doing a simplified analysis, just saying we're going to ignore by making these resistor values small, we're going to ignore I sub b. So let me jump to the punchline. This biasing circuit is better, but we still have somewhat of a problem with it, and I'll talk about one. But just going back, what we did was we said, okay, we're going to make R1 and R2 small enough that the current through them is going to be much higher than I sub b, and we can ignore I sub b. But if you wanted to actually calculate what would the effect that I sub b would have, you do a Thevenin equivalent of this, and then you would sort of replace this with the Thevenin equivalent, and, you know, sort of actually calculate what would happen here with different I sub b values. I'm going to leave that. It's, you know, there's an example of it in the book and a description of it in the book. All you're doing is you're changing this into the Thevenin equivalent and using that in your model here. Okay, so if somebody here wants to see it, I can work it through, but anyway, I was just gonna kind of skip it. And you know, it's pretty sort of straightforward, and there's an example in the book. So anybody desperate for me to do an example of this? Not hearing you yet.
I just have one question. So the R1 and R2 thing on the left, we just switched that to Thevenin?
Yes.
Yeah. Okay.
Yeah. So this guy. Yeah. So that's what you do. Switch that to a Thevenin. So basically your model, so this guy, you model it as a Thevenin equivalent. So that way you can actually include the effects of R sub b in calculating your V sub x. Does that
Will the steps on doing that be kind of covered just by going through the homework?
I don't remember now. Maybe.
Isn't it? Well, isn't it just like, isn't it the same way we always have done V Thevenin in other classes and stuff? No.
Yeah, it'll be similar. Yeah. It's not, Brandon, it's not my favorite thing, so it's not going to show up on the test.
Oh, okay.
Okay, so I mean, for your amusement, you could, I mean, again, I'm happy to follow it, but it's covered pretty well in the book about how to do the Thevenin, and like, anyway, it's covered pretty good with an example, etc. I don't remember if I have a homework problem, but again, I think what the point I'm kind of gonna make is that this isn't really quite, you know, we could get into like a deep analysis of this thing, but in fact, I'm saying like, I'm kind of saying don't use this in real life. So I don't want to spend a lot of more time sort of analyzing it, if that makes sense.
It's an unnecessary analysis that doesn't really need to take place in the real world, is kind of what you're saying.
Yeah, I mean, I'm like, because, the next thing I'm gonna say is why this is not such a hot circuit either. So, like, we could, there's an analysis of it in the book, but I'm like, hey, man, I'm just like, why, right? So, so anyway, so let me first say why it's not such a hot circuit is because we still have a problem. The problem is that these resistor values are also not, if you're in production, so it's easy for me to say in this example that this is 17 kilo ohms and this is 8 kilo ohms. But as you guys may or may not know, when you buy resistors or when you make them or whatever, you don't get these absolute values. There's variations also in resistor values from resistor to resistor. So if you buy resistors, like if you go and buy, say, 17 kilo ohm resistors, you're gonna get them either with 10% variation, or if you want to pay more, you'll get them with 1% variation. Okay, so basically it's not as bad as beta, thank God, but you might get, even if you pay the extra, I mean, depends on your product. Each resistor is not going to be that much more. I don't know what a 1% variation resistor is going to cost you, but remember, you're going to use lots of these in your circuit, in your product. By lots, I mean maybe hundreds or thousands. And so, and your product price point, God knows, maybe, might be fairly expensive, but even if it's 1%, you could easily get 1% variation here for this. So this guy might have easily like 1% or more variation, depending on the resistor types used. And the problem is that your I sub C is exponentially dependent on this value. Okay, so remember, I sub C is I sub S exponential of, in this case, V sub X over VT. Okay, so it means that if, small changes in V sub X from part to part, from product to product you're making, is going to have some really drastic consequences for I sub C. Okay, and if I sub C is varying all sorts of places, then again, because of this exponential, a small change here could have a drastic consequence. So like, what is so you could have a big change on I sub C. And what that means is you could have a big change in the gain, because I sub C is varying quite a bit. No, I'm not even talking about 10%. 10% change would be just, I mean, imagine 10% of 850 millivolts is like 85 volts. So that's a factor. This is a good thing to remember. If V sub X changes by 60 millivolts, I sub C is going to change by a factor of 10. So, instead of being 231 microamps, it would be 2.3 milliamps. Okay, if this guy changes by only 60 millivolts. So that's the problem with this thing, is variations in R1 and R2, and the fact that I sub C is exponentially dependent on V sub X makes this thing not the perfect choice. Okay, because that's sort of the next layer you have to worry about. Okay, so I'm gonna so the next lecture we're gonna add one more resistor and show how that is gonna give you guys the sort of the practical biasing approach. And also lead us to this concept of emitter degeneration. Okay, guys, any questions? No?
I'm pretty sure you said this in the other thing, or other one. What is V sub X in relation to VBE? Because we're treating them as the same.
Yeah, in
most
this, as long as you have, as long as the emitter is grounded, so V sub X is here, so that's the base emitter voltage.
Okay, yeah, as
Yeah.
long as it's grounded.
As long as grounded, yeah. So for example, in this case,
There's another resistor.
yeah, this is V sub X would not be equal to VBE because the emitter won't be at ground.
Okay. Thank you.
Sure. Any other questions, guys? Okay, well, have a great weekend. Take care. Ooh,
You too,
Well,
Professor.
take care. Elizabeth, I've been bad. I haven't started grading yet, so I'm not sure. I'll be grading this weekend. Take care, guys.